Tonight we are going to talk about something that should not exist, not in the way that dark matter should not exist. We are talking about black holes so massive, so incomprehensibly large, that even the theories we have for how black holes grow cannot fully explain them. Objects that break our models not by being slightly outside the expected range, but by being so far beyond it that the gap itself becomes the mystery. We covered ton 618 in a previous video. And if you watched that one, you already know how difficult it is to hold that number in your mind. Ton 618 has a mass of 66 billion times the mass of our Sun. 66 billion solar masses packed into a single object, a single point of no return at the heart of a quasar more than 10 billion light-years away. We spent an entire video trying to give you a genuine sense of what that means, and by the end of it, most of you probably agreed that human intuition simply stops working at those scales. But ton 618 is not the end of the story. It is not the largest, the strangest, or the most difficult to explain. It is not even close to the edge of what we have found. Because the universe, as it turns out, has been doing things with black holes that our best models of black hole growth did not predict. Things that force us to go back to the beginning and ask a question that sounds embarrassingly simple for a field as advanced as modern astrophysics. How do black holes get this big? That is what tonight is about. Not just the scale. Not just the numbers, though we will absolutely sit with the numbers because they deserve to be sat with. Tonight is about the physics underneath the scale, about what it means for a black hole to be too massive to exist according to our models, about what the existence of these objects tells us about the early universe, about the nature of gravity, and about how much we still do not understand about the structures that anchor entire galaxies. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It is a small thing for you, but it makes a huge difference for me. Now make yourself comfortable. Let us begin. Let us start with something you think you understand: a black hole. You probably have a mental image of one, a dark sphere, perhaps with a glowing ring of light around it, the accretion disk, the material spiraling inward, heating up, glowing white-hot before it crosses the point of no return. You might picture the event horizon, the invisible boundary beyond which nothing, not light, not information, not anything can escape. You might picture the singularity at the center, the point where our mathematics breaks down and density becomes, in the equations at least, infinite. That image is not wrong, but it is incomplete in a way that matters for what we are about to discuss. Because a black hole is not just a drain in space. It is not just an object that pulls things in. It is a region of spacetime so severely curved by mass that the geometry of space itself closes off around it. To understand why some black holes are too large to exist according to our models, you need to understand not just what a black hole is, but how black holes grow. And to understand that, you need to understand where they come from in the first place. The black holes we are most familiar with form when massive stars die. A star is, throughout its life, a balancing act. On one side, gravity, the enormous self-gravity of the star's own mass, pulling everything inward, trying to collapse the star into the smallest possible volume. On the other side, the outward pressure from nuclear fusion in the core. As long as there is fuel to burn, as long as fusion is happening, the radiation pressure pushes back against gravity and the star maintains its size. It is a stable equilibrium, maintained for millions or billions of years depending on the star's mass. But when the fuel runs out, the equilibrium breaks. gravity wins. The core collapses in a fraction of a second. If the star is massive enough, the collapse does not stop at a neutron star. It continues past every known form of resistance, past the point where even the quantum mechanical pressure between neutrons can halt it, and a black hole forms. The event horizon appears. Everything inside it is cut off from the rest of the universe. These are called stellar mass black holes. They typically have masses between roughly 5 and a few tens of solar masses. Some, formed from the most massive stars, can be somewhat larger, but they are bounded. They are the product of a single stellar death, and the mass available to them is limited by the mass of the star that formed them. At the other end of the scale, sitting at the centers of virtually every large galaxy in the universe, are the objects we are going to spend tonight with: supermassive black holes. These are not just big versions of stellar black holes. They are different in ways that matter. They range in mass from about 1 million solar masses at the low end to, in the most extreme cases, tens of billions of solar masses at the high end. The black hole at the center of our own Milky Way, called Sagittarius A star, has a mass of about 4 million solar masses. The black hole at the center of the giant elliptical galaxy M87, the one we imaged directly for the first time in 2019, has a mass of about 6.5 billion solar masses. These are already numbers that dwarf any stellar mass black hole by factors of millions. And then there are the ones that go beyond even that, the ultramassive black holes. The ones that should not, strictly speaking, exist at the sizes they do given the age of the universe and the rates at which we believe black holes can grow. Ton 618 at 66 billion solar masses. Holm 15A star at roughly 40 billion solar masses. Phoenix A at an estimated 100 billion solar masses, though that measurement carries significant uncertainty. These are the objects we need to talk about tonight. But before we can talk about why they are surprising, we need to talk about how black holes grow, because it is only against the backdrop of what our models predict that the existence of these objects becomes truly strange. Black holes grow by eating. That is the simple version. Matter falls in, the mass increases, the event horizon grows. The event horizon of a non-rotating black hole, called a Schwarzschild black hole, has a radius that is directly proportional to its mass. Double the mass and you double the radius of the event horizon. It is a linear relationship. This means that as a supermassive black hole grows, its event horizon expands. A black hole with the mass of 1 billion suns has an event horizon with a radius of about 3 billion kilometers. That is about 20 times the distance from the Earth to the Sun. The event horizon of Ton 618 is roughly the size of our entire solar system out to the orbit of Neptune, times a factor of several hundred. But eating has a limit. And this limit is one of the most important constraints in all of astrophysics. It is called the Eddington limit. Here is the problem. When matter falls toward a black hole, it does not fall in cleanly and quietly. The infalling material forms an accretion disk, a swirling structure of superheated gas and plasma. As this material heats up, it radiates, it glows. It emits light, X-rays, ultraviolet radiation, an enormous output of electromagnetic energy. And that radiation pushes back. It exerts pressure on the infalling material. Radiation pressure, the force of light itself pushing against matter. At a certain accretion rate, the radiation pressure becomes so strong that it balances gravity. Material that tries to fall in gets blown back out by the radiation from material already falling in. the black hole cannot eat any faster than this. The rate at which it can grow is self-limited by its own luminosity. This maximum rate is the Eddington limit, named after the British astrophysicist Arthur Eddington, who first worked out the mathematics in the 1920s. The Eddington limit has a direct implication for how quickly a black hole can grow. If you start with a black hole of a given mass and let it grow at the Eddington limit continuously, you can calculate how long it takes to reach any given final mass. And this calculation is where the problem begins. The universe is 13.8 billion years old, but the most distant quasars we observe, powered by supermassive black holes with masses of billions of solar masses, are seen at redshifts corresponding to times when the universe was less than 1 billion years old. Some of them are seen when the universe was only a few 100 million years old. A few 100 million years after the Big Bang, some black holes already had masses of billions of solar masses. Work through the Eddington limit calculation, and you find that starting from a stellar mass black hole of a few tens of solar masses, growing continuously at the Eddington limit, you cannot reach 1 billion solar masses in a few 100 million years. The time is not enough. The math does not work, not even close. This is not a minor discrepancy. It is not a rounding error or a measurement uncertainty. It is a fundamental tension between what we observe and what our models predict. And it gets worse when you consider that real black holes almost certainly do not grow at the Eddington limit continuously. Real accretion is episodic. It turns on and off. Galaxies merge, feeding the central black hole with new material, and then the feeding stops. A black hole that grows episodically, not continuously, grows even more slowly than one growing at the theoretical maximum rate. And yet the universe is full of black holes that are far too massive to have formed this way. So where did they come from? This is the question that drives much of modern astrophysics research into black holes, and there are several proposed answers, each with different implications for what the early universe looked like. The first possibility is that we are wrong about the initial seed. If stellar mass black holes, a few tens of solar masses, are the starting point, and the Eddington limit constrains the growth rate, then we need either a larger starting seed or more time or both. Some researchers propose that the seeds were not stellar mass black holes at all, but much larger objects formed directly from collapsing clouds of gas in the early universe. These are called direct collapse black holes, or DCBHs. The idea is that in the early universe, under certain conditions, enormous clouds of pristine hydrogen gas could collapse directly into a black hole without first forming a star. The resulting object could have a mass of tens of thousands to perhaps 100,000 solar masses, with a larger seed growing to 1 billion solar masses within the age constraints becomes more feasible. The problem is that we have not directly observed direct collapse black holes. They are theoretically motivated, and there are some candidate objects that might be consistent with them, but we do not have a confirmed detection. They remain a hypothesis, a well-motivated one, but not yet an established fact. The second possibility is that the Eddington limit is not as firm as we thought. It is, after all, derived under specific geometric assumptions about how accretion works. If the geometry of the accretion disk is different from what the standard model assumes, if material can fall in through certain channels while radiation escapes through others, then the Eddington limit can be exceeded. This is called Super-Eddington accretion, and there is observational evidence that it occurs in some systems. Certain ultraluminous X-ray sources show signatures consistent with accretion rates well above the Eddington limit. If early supermassive black holes routinely underwent episodes of Super-Eddington accretion, even briefly, they could grow much faster than the standard model predicts. The third possibility is mergers. Two black holes can merge to form a larger one. If the seeds were numerous and compact enough, and if they merged efficiently in the dense environments of early galaxies, then the cumulative growth from mergers could supplement accretion and produce very large black holes more quickly. But mergers have their own efficiency constraints. When two black holes merge, the gravitational wave emission from the merger can impart a recoil kick to the resulting black hole, potentially ejecting it from its host galaxy. And the mechanics of how two supermassive black holes in merging galaxies actually spiral close enough to merge, crossing what is called the final parsec, is itself an unsolved problem. The truth is probably some combination of all of these. Large seeds, episodes of Super-Eddington accretion, and mergers, all contributing to the growth of the largest black holes we see today. But the specific combination, the relative importance of each pathway, is not yet determined. We are still working it out. Now let us turn to the specific objects that make this problem most acute. Because the ultramassive black holes, the ones at the extreme end of the mass distribution, pose challenges that go beyond just the time available for growth. They pose challenges to our understanding of how galaxies and black holes co-evolve. Here is something remarkable. There is a tight relationship between the mass of a supermassive black hole and the properties of the galaxy that hosts it. Specifically, the mass of the black hole correlates tightly with the mass of the central bulge of its host galaxy, and with the velocity dispersion of stars in that bulge. This correlation, called the M-sigma relation, holds across many orders of magnitude in black hole mass. It tells us that somehow, the black hole and its host galaxy grew together, that they influenced each other's development, that they are not independent objects but co-evolving systems. The mechanism behind this co-evolution is thought to be feedback. When a black hole is actively accreting material, the energy it releases in the form of radiation, jets, and winds can heat the surrounding gas, blow it out of the galaxy, and suppress star formation. This feedback regulates both the growth of the black hole and the growth of the galaxy. Too much accretion, and the feedback becomes so powerful that it shuts off the gas supply, stopping further growth. The system reaches an equilibrium determined by the interplay between gravity and feedback. If this picture is correct, then the mass of a supermassive black hole is not arbitrary. It is set by the physics of feedback in its host galaxy. And the most massive black holes should live in the most massive galaxies, galaxies where the gravitational potential is deep enough that even powerful feedback cannot completely shut off the gas supply. And this is largely what we see. The most massive black holes we know of sit in the most massive galaxies. Holm 15A star, with its estimated mass of 40 billion solar masses, sits at the center of a giant elliptical galaxy in the Abell 85 cluster, one of the most massive galaxies known. The host galaxy itself is estimated to have formed through multiple major mergers over cosmic time, and the black hole's extreme mass may reflect this merger history. But the ultramassive black holes push even this framework. At 40 billion, 66 billion, potentially 100 billion solar masses, These objects are more massive than our models of feedback-regulated growth straightforwardly predict for even the largest galaxies. Something about the formation history of these objects is extreme. Either they experienced unusually efficient accretion, or they formed from unusually massive seeds, or they benefited from an unusually rich merger history, or some combination of all three. Let us talk about Holm 15A star specifically, because it is one of the best measured ultramassive black holes, and its properties are genuinely extraordinary. The galaxy hosting Holm 15A star, officially designated Holm 15A, is a giant elliptical galaxy at the center of the Abell 85 galaxy cluster, about 700 million light-years from Earth. It is already one of the most massive galaxies known. Its central region has an unusual structure. The density of stars at the center drops off more steeply than in typical giant elliptical galaxies, forming what astronomers call a core, an evacuated region where the stellar density is lower than expected. This kind of core is thought to form when two supermassive black holes, brought together by a galaxy merger, form a binary system and gradually spiral toward each other. As they orbit each other, they gravitationally scatter stars out of the central region. The stars gain energy and are ejected from the core, while the black holes lose energy and slowly spiral inward. The larger the binary, the more stars get ejected, and the larger the resulting core. The core of Holm 15A is enormous. It is one of the largest stellar depleted cores ever observed, with a radius of roughly 15,000 light-years. This huge core is itself evidence that the central black hole went through an extreme merger history, that the black hole we see today is the result of multiple major mergers over cosmic time, each one scouring out more of the central stellar population. The mass of the black hole was estimated using stellar dynamics. Astronomers measured how fast stars move in the central region of the galaxy. The faster the stars move, the deeper the gravitational potential well, and the more mass must be concentrated in the center to account for those velocities. Working through the dynamics carefully, the estimated mass came out to roughly 40 billion solar masses, with significant uncertainty. The measurement is not as clean as we would like, because at the center of such a massive galaxy, with such a large depleted core, the stellar population is not as dense as in smaller galaxies, making the kinematic measurements more challenging. But even accounting for the uncertainties, the mass is extraordinary, 40 billion solar masses. Let me try to give you a sense of what that means. The mass of our entire Milky Way galaxy, stars, gas, dust, dark matter, everything, is estimated at roughly 1 to 2 trillion solar masses. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million solar masses. That means Sagittarius A star contains about 4 millionths of the total mass of the galaxy. It is a tiny fraction of the whole. Holm 15A star contains about 40 billion solar masses. Its host galaxy has a total mass estimated at roughly 2 trillion solar masses, so the black hole at its center contains about 2% of the total mass of the entire galaxy, 2% compared to 4 millionths for our own galaxy's black hole. The black hole at the center of Holm 15A is not a small fraction of its host galaxy. It is a significant component of it. And the event horizon of this object, the boundary of no return, has a radius of roughly 120 billion kilometers. In astronomical units, that is about 800 astronomical units. The average distance from the Earth to the Sun is 1 astronomical unit. The edge of the solar system, where the Voyager probes are now traveling after decades of flight, is roughly 120 astronomical units. The event horizon of Holm 15A star extends to more than 6 times the distance Voyager has traveled since launch. The event horizon itself is larger than many solar systems. Now let us talk about the object that currently holds, with some uncertainty, the record for the most massive black hole ever measured. Phoenix A is a giant elliptical galaxy at the center of the Phoenix galaxy cluster, about 5.8 billion light-years from Earth. It is already remarkable for other reasons. It hosts one of the most powerful active galactic nuclei ever observed, pumping out an enormous amount of energy. The jets from its central black hole excavate enormous cavities in the hot gas that fills the galaxy cluster. Cavities so large they can be seen in X-ray observations as regions of reduced emission. The estimated mass of the black hole at Phoenix A's center is somewhere around 100 billion solar masses. That number carries large uncertainties. It is not measured through stellar dynamics the way Holm 15A star is, because the galaxy is too distant for those measurements to be feasible with current instruments. Instead, the mass is estimated from the properties of the jets and the energy output of the system, methods that are less direct and carry larger systematic uncertainties. But even if the true mass is half of 100 billion, it is still 50 billion solar masses. Even if it is a quarter, it is 25 billion solar masses. Any of these numbers places Phoenix A among the most massive black holes ever observed, and all of them strain our models of how black holes grow. A black hole of 100 billion solar masses, if we take the estimate at face value, would have an event horizon radius of roughly 200 billion kilometers. In a very real sense, this single object is larger than many of the distances we use to describe our local cosmic neighborhood. The distance from the Sun to the nearest star, Proxima Centauri, is about 40 trillion kilometers. The event horizon of Phoenix A is about half that distance. We are talking about an object whose edge is comparable to the gap between nearby stars. These numbers are not just impressive, they are physically meaningful. They tell us something about the depth of the gravitational well, the strength of the tidal forces near the event horizon, the behavior of spacetime in the vicinity of these objects. Near the event horizon of a stellar mass black hole, tidal forces are extreme. An astronaut crossing the event horizon of a 10 solar mass black hole would be shredded by the tidal forces, the difference in gravitational pull between their head and feet, long before they reached the boundary. But the event horizon of a supermassive or ultramassive black hole is so large that tidal forces at the horizon itself are relatively gentle. An astronaut could cross the event horizon of a billion solar mass black hole without immediately feeling anything unusual. There would be no dramatic moment, no visible boundary, no sensation of crossing a threshold. The crossing would be from the inside invisible. What would be visible from a safe distance is the accretion disk. The material spiraling into these ultramassive black holes forms accretion structures of enormous scale. The temperature and luminosity of these structures depend on the accretion rate. When these black holes are actively feeding, as they are in quasar phases, they can outshine entire galaxies. A quasar powered by a supermassive black hole can have a luminosity equivalent to trillions of solar luminosities, concentrated in a region smaller than our solar system. The most luminous quasars ever observed are powered by black holes similar in mass to the ones we are discussing tonight. But most of the ultramassive black holes we know about today are not in active quasar phases. They are quiet, dormant, or at least much less active than they were in their youth. The black hole at the center of Holm 15A is not currently powering a bright quasar. Neither is Sagittarius A star. These black holes went through their most active growth phases billions of years ago, when the universe was younger and there was more gas available for accretion. Now they sit at the centers of their host galaxies, their event horizons spanning hundreds of billions of kilometers, surrounded by the depleted cores they created through their merger histories, relatively quiet in the present epoch. This quietude is itself informative. It tells us about the life cycle of black holes, about how the relationship between a black hole and its host galaxy changes over time. In the early universe, when galaxies were gas-rich and mergers were frequent, black holes could grow rapidly. As the universe aged, as galaxies consumed their gas and mergers became less frequent, the fuel supply for black hole growth declined. The Great Quasar Era, when the universe was teeming with actively accreting supermassive black holes, peaked when the universe was about 2 to 3 billion years old. Since then, the overall activity has declined, and the most massive black holes have largely settled into their current dormant states. But dormant does not mean dead. These black holes are still there. They are still accumulating mass slowly from whatever material drifts into their vicinity. The event horizon continues to grow, imperceptibly slowly on human timescales, and occasionally a disruption event occurs. A star wanders too close, torn apart by tidal forces before it can cross the event horizon, with some of the stellar debris forming a temporary accretion disk and producing a burst of radiation visible across billions of light years. These tidal disruption events give us a way to detect and study black holes that are otherwise too quiet to observe directly. For the most massive ultramassive black holes, even tidal disruption events have unusual properties. The tidal radius, the distance from the black hole at which a star is disrupted, depends on the mass of the black hole and the properties of the star. For very massive black holes, the tidal radius can actually be inside the event horizon. This means that for the most massive black holes, a star can fall all the way to the event horizon and cross it before being tidally disrupted. It swallows the star whole, rather than shredding it outside the horizon. These events produce a different signature than typical tidal disruption events, and understanding the statistics of tidal disruptions can itself tell us about the mass distribution of ultramassive black holes. Now, I want to take you somewhere that requires a different kind of thinking. Away from the observational evidence, away from the specific objects we have cataloged, and toward the question of what these black holes mean for physics at its most fundamental level. A black hole is a singularity problem. At the center of every black hole, according to general relativity, there is a singularity, a point where the density is infinite, where the curvature of spacetime is infinite, where the equations that describe the smooth geometry of spacetime break down entirely. The singularity is not a physical object in any conventional sense. It is a place where the theory fails. It is a sign that general relativity is incomplete, that at sufficiently extreme conditions, some other theory, some quantum theory of gravity, must take over. For stellar mass black holes, the singularity is far inside the event horizon, buried under enormous distances of spacetime geometry. For ultramassive black holes, the event horizon is enormous, but the singularity is still there at the center. The physics at the singularity does not depend on the size of the black hole in a simple way. What changes is the density at the event horizon. For a stellar mass black hole, the average density inside the event horizon is enormous, greater than nuclear density. But for a sufficiently massive black hole, the average density inside the event horizon can actually be quite low. A black hole with a mass of about 10 billion solar masses has an average density inside its event horizon roughly equal to the density of water. An ultramassive black hole of 100 billion solar masses has an average density inside its event horizon even lower than that. This seems paradoxical. A black hole with the average density of water, but it makes sense when you think carefully about what the event horizon represents. The event horizon is not a surface where matter is concentrated. It is a mathematical boundary, the surface of no return, defined by the geometry of spacetime. The mass of the black hole is concentrated at the singularity. The event horizon is just where the escape velocity reaches the speed of light. And for a more massive black hole, the event horizon is proportionally larger, so the mass is spread over a much larger volume on average. This has a remarkable implication. If there existed a region of space dense enough to form a black hole, but with a very gentle gradient of density, not a point mass, but an extended region of slightly above critical density, an observer inside that region might not immediately notice they were inside a black hole. The locally measured density would be low, the tidal forces gentle, the geometry nearly flat. Only by trying to escape, by trying to send signals out, would they discover that they were trapped. This thought experiment, scaled up to cosmic proportions, actually forms part of the basis for certain models of cosmology and has inspired some of the more exotic ideas about the nature of our own universe. But let us come back to what we know and to what the existence of these ultramassive objects tells us about the cosmos. One of the most important implications is for our understanding of galaxy formation and evolution. The discovery of very massive black holes at high redshift, when the universe was very young, tells us that the first structures to form in the universe were not just early galaxies, but early massive black holes. The seeds of these objects must have formed very quickly after the Big Bang, and they must have grown very rapidly in the dense, gas-rich environments of the early universe. This has driven a whole new area of research into what cosmologists call the high redshift universe, the universe as it was in its first billion years. The James Webb Space Telescope, launched in December 2021 and operational since mid-2022, has already transformed our understanding of this era. Webb can see galaxies and quasars at redshifts higher than any previous observatory, looking back to times when the universe was only a few 100 million years old. And what it is finding is challenging our models. Webb has detected galaxies at extreme redshifts that are more massive and more evolved than models predicted they should be. It has found actively accreting black holes in the early universe that appear to be growing faster than the Eddington limit would allow in standard models. It has revealed a high redshift universe that is, in some respects, more structured and more complex than our pre-Webb picture suggested. This does not mean our cosmological models are wrong in their broad strokes. The Big Bang, cosmic inflation, the formation of structure through gravitational collapse, these remain robust. But the details of how the first galaxies and the first supermassive black holes formed and grew, the details that determine the mass distribution we observe today, those details are being revised and refined in real time as Webb data comes in. The black holes that should not exist, the ultramassive black holes that are too large for our models, are not anomalies to be explained away. They are clues. They are the universe telling us something about its own history that our models have not yet fully captured. Understanding them requires understanding the earliest moments of cosmic structure formation, the physics of the first stars and the first black holes, the mechanisms by which ordinary matter and dark matter interact in the dense environments of early galaxies. And understanding them has implications that extend beyond just black hole physics. The relationship between black holes and galaxies, the feedback mechanisms that regulate star formation, the way energy flows between the smallest scales of particle physics and the largest scales of cosmic structure. All of this is illuminated by studying the most extreme objects the universe has produced. There is something philosophically striking about what we are discussing. The universe has been running an experiment for 8 billion years under conditions we cannot replicate in any laboratory, with outcomes we can only partially observe. And the results of that experiment include objects like Holm 15A star and Phoenix A, objects so massive that they are the most gravitationally dominant single things in their local universe. Objects whose event horizons span distances comparable to the gaps between nearby stars. Objects that grew from nothing to their present enormity through processes we are still working to understand, over timescales that dwarf the entire history of complex life on Earth. In all of this, every one of these objects, every measurement, every theoretical framework we have brought to bear on the question of how they formed and what they are, all of it points to the same conclusion. We are still at the beginning. We are still in the early stages of understanding what black holes are at the most extreme end of the mass distribution, what they tell us about the early universe, and what they imply about the physics of gravity and spacetime at its most extreme. The black holes that should not exist are there. We have measured them. We have imaged some of them, or at least their shadows. We have detected the gravitational waves from merging stellar mass black holes, and we are preparing instruments to detect the gravitational waves from merging supermassive black holes, which will ring through spacetime at frequencies far below what current detectors can hear, but which future space-based observatories like LISA will be able to pick up. Every new measurement adds to the picture. Every new observation constrains our models a little more tightly. And every time we think we have a handle on it, the universe shows us something at the extreme end of the distribution that forces us to think again. That is not a failure of science. That is what science looks like when it is working. The black holes that should not exist are not a problem to be solved and forgotten. They are an ongoing invitation to go deeper, to push our models harder, to ask better questions about the nature of the most extreme objects the universe has ever produced. We have come a long way from the first theoretical prediction of black holes in the early 20th century. We have come a long way from the first observational evidence that supermassive black holes exist at the centers of galaxies. We have come a long way from the first image of a black hole shadow, released in 2019. And we have a long way still to go before we fully understand what the universe has been building in the dark, at the centers of galaxies, over billions of years of cosmic time. The black holes that should not exist are out there. And the fact that they exist, the fact that they pushed beyond what our models said was possible, is one of the most important things the universe has ever told us about itself. We just have to keep listening. Sleep well tonight knowing that at the center of almost every galaxy, including our own, something enormous and ancient and still not fully understood is sitting quietly in the dark, waiting, growing imperceptibly slowly, one infalling star at a time. The universe has been building these things for longer than the Earth has existed, and we are only just beginning to understand what they are. Good night. There is a number that keeps coming up in discussions of the most massive black holes, and I want to spend some time with it because it illustrates something important about the relationship between mass and geometry in general relativity, the Schwarzschild radius. Named after the German physicist Karl Schwarzschild, who derived the first exact solution to Einstein's field equations in 1916, just months after Einstein published General Relativity, while Schwarzschild himself was serving on the Russian front during the First World War. He derived it and sent it to Einstein from the trenches, and died a few months later from an illness contracted at the front. The solution he found described the geometry of spacetime around a spherically symmetric mass, and it contained, buried in the mathematics, the concept that would eventually become the black hole. The Schwarzschild radius of an object is the radius to which you would have to compress it for it to become a black hole. Compress the Earth to a sphere about the size of a marble and it becomes a black hole. Compress the Sun to a sphere about 3 kilometers across and it becomes a black hole. The Schwarzschild radius is proportional to mass. Double the mass and you double the Schwarzschild radius. For the ultramassive black holes we have been discussing, the Schwarzschild radius is the event horizon radius. It is the physical scale of the object, in the only sense that matters for a black hole. And for Holm 15A star, with a mass of 40 billion solar masses, the Schwarzschild radius is roughly 120 billion kilometers. For Phoenix A, if its mass is truly around 100 billion solar masses, the Schwarzschild radius is roughly 300 billion kilometers. 300 billion kilometers. That is 3 times 10 to the 14th meters. In light travel time, it is about 5 days. Light traveling at 300,000 kilometers per second takes more than 11 days to cross from one side of the event horizon to the other. Sit with that for a moment. The event horizon of Phoenix A, the boundary of no return of a single object, is so large that light takes almost 2 weeks to cross it. In the same time that light is crossing the event horizon of this black hole, on Earth, a person could fly from one continent to another many hundreds of times. The entire history of human civilization would fit into a small fraction of the time it would take light to traverse this object. These comparisons do not capture the reality, because no comparison does, but they gesture toward it. They show you why these objects are not just quantitatively extreme, but qualitatively different from anything in human experience. They represent a regime of physics where our everyday intuitions are not just stretched but completely inapplicable, and yet they are real. They exist. They are out there at the centers of galaxies hundreds of millions or billions of light years away, sitting quietly in the dark, their event horizons spanning distances that dwarf entire solar systems. The universe made them. The universe ran the physics for billions of years, and these are what came out. How did they get there? We have talked about the proposed mechanisms. direct collapse seeds, Super-Eddington accretion, mergers. But I want to go deeper into the merger scenario because it connects to one of the most exciting observational frontiers in modern physics. When two galaxies merge, a process that takes hundreds of millions of years, the supermassive black holes at their centers do not immediately merge as well. They start out separated by tens of thousands of light years, the typical separation between the centers of two merging galaxies. Over time, dynamical friction, the gravitational drag exerted on a massive object moving through a sea of stars and dark matter, causes the black holes to lose energy and spiral toward each other. This process can bring them from tens of thousands of light years apart to a few light years apart relatively efficiently. But then something happens. Or rather, something stops happening. At separations of around a parsec, a few light years, dynamical friction becomes less effective. There are simply not enough stars in the right place to continue efficiently extracting angular momentum from the black hole binary. The black holes stall. This is the final parsec problem, one of the outstanding puzzles in the field of supermassive black hole mergers. Various mechanisms have been proposed to solve the final parsec problem. A triaxial galaxy potential, one that is not perfectly spherically symmetric, can continue to supply stars on lost cone orbits to interact with the binary. Gas accretion can provide a torque that extracts angular momentum. A third black hole, brought in by a subsequent galaxy merger, can gravitationally interact with the binary and cause it to harden further. The evidence from the large depleted cores of galaxies like Holm 15A suggests that some binaries do eventually merge, because the size of the depleted core reflects the hardening and eventual merger of a massive binary. But the mechanism by which they make it through the final parsec is not definitively established. When a supermassive black hole binary does merge, the event releases an enormous amount of energy in the form of gravitational waves, not the short, sharp chirps that LIGO detects from stellar mass black hole mergers, which last fractions of a second at audio frequencies, but long, slow, deep rumbles at frequencies far below what any ground-based instrument can detect. A merging binary of 2 billion solar mass black holes would emit gravitational waves at frequencies of nanohertz, billionths of a cycle per second. A single cycle would take years to complete. Detecting these waves requires a different approach, the pulsar timing array. The idea is to use millisecond pulsars, rapidly spinning neutron stars that emit radio pulses with extraordinary regularity, as the arms of a gravitational wave detector. As a gravitational wave passes through the Earth, it stretches and compresses space, and this stretching and compressing introduces tiny, correlated changes in the arrival times of pulses from pulsars in different directions. By monitoring an array of millisecond pulsars distributed across the sky and looking for these correlated timing variations, you can detect gravitational waves in the nanohertz frequency band. In 2023, multiple pulsar timing array collaborations, the North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Chinese Pulsar Timing Array, all announced strong evidence for a gravitational wave background in the nanohertz band. A background of gravitational waves is exactly what you would expect if there are supermassive black hole binaries merging throughout the universe at various stages of their merger. The gravitational waves from all these different mergers, occurring at different times and in different directions, superpose to create a stochastic background, a hiss of gravitational radiation filling the entire universe. The signal detected by the pulsar timing arrays is consistent with this interpretation. It is consistent with the expected background from a population of merging supermassive black hole binaries. If confirmed, and the evidence is already quite strong, this would be the first direct detection of gravitational waves from supermassive black hole systems, and it would open an entirely new observational window on the most massive objects in the universe. Future pulsar timing array observations, with more pulsars monitored over longer baselines, should be able to move from detecting the background to potentially resolving individual sources. The loudest merging binaries in the universe might eventually stand out above the background and be detected individually. And the planned space-based gravitational wave observatory, LISA, scheduled for launch in the 2030s, would be sensitive to merging binaries of millions to billions of solar masses at frequencies between the pulsar timing array band and the LIGO band. LISA could detect merging supermassive black hole binaries in real time as they spiral together and merge, providing a direct observational window on the most energetic events in the universe. This is the future of black hole physics. Not just cataloging the most massive objects, but watching them interact, merge, and grow in real time, or at least as close to real time as the speed of light allows. Seeing the processes that built the ultramassive black holes we observe today playing out across the universe, documented by a new generation of instruments sensitive to the gravitational wave signatures of the most extreme events in cosmic history. We are at the beginning of this era. The pulsar timing array results are a first detection, a proof of concept, a demonstration that the gravitational wave background from supermassive black hole mergers is real and detectable. LISA will take it to the next level. And beyond LISA, there are proposals for even more ambitious space-based gravitational wave observatories that could eventually map the entire population of merging supermassive black holes across the observable universe. The black holes that should not exist are not just objects to be cataloged. They are laboratories. They are the most extreme tests of general relativity available in the observable universe. The behavior of spacetime near the event horizon of a 100 billion solar mass black hole is, in principle, calculable from Einstein's equations, but it is also, in some respects, qualitatively different from what happens near a stellar mass black hole. The scale of the system is different. The density at the horizon is different. The dynamical timescales are different. And the relationship between the black hole and its environment, the host galaxy, the intracluster medium, the surrounding large-scale structure, is different in ways that matter for how the black hole grows and evolves. Understanding these differences, pushing our theoretical frameworks to the limits imposed by the most extreme observations, is how physics advances. Not by finding that our theories work in easy cases, but by testing them in the hardest cases, the most extreme environments, the most massive objects, and seeing whether they hold up or whether they crack. And when they crack, seeing what the crack tells us about what lies beyond. General relativity has not cracked yet, not in the observational tests we have been able to perform. The images of black hole shadows are consistent with general relativity. The gravitational wave signals from merging black holes are consistent with general relativity. The dynamics of stars near Sagittarius A star are consistent with general relativity. The theory continues to pass every test we can throw at it, but we have not yet tested it in the regime closest to the singularity. We have not yet probed the physics of quantum gravity, the regime where the curvature of spacetime becomes so extreme that quantum effects become important and general relativity must give way to some deeper theory. The singularity at the center of every black hole is where this regime is reached, and it is, by definition, hidden from us behind the event horizon. Whatever happens at the singularity stays at the singularity, or does it? There is a theoretical argument developed by Stephen Hawking in the 1970s that black holes are not completely black. That quantum effects near the event horizon cause black holes to radiate very slowly, at a temperature inversely proportional to their mass. For a stellar mass black hole, the Hawking temperature is so low, a fraction of a billionth of a Kelvin above absolute zero, that it is utterly undetectable against the cosmic microwave background radiation. For an ultramassive black hole, the temperature is even lower, even more imperceptibly small. Hawking radiation has never been directly detected. We cannot detect it. The signal is too weak, but it has profound theoretical implications. If black holes radiate, they lose mass over time. Eventually, very, very slowly, on timescales vastly longer than the current age of the universe, a black hole will evaporate completely. And this evaporation raises a deep question in quantum mechanics. What happens to the information about everything that fell into the black hole? Is it destroyed? Is it encoded in the radiation? Does it come out somehow at the end? This is the black hole information paradox, and it remains one of the deepest unsolved problems in theoretical physics. Its resolution requires a reconciliation of quantum mechanics and general relativity, the two pillars of modern physics that are, in their current forms, incompatible with each other at the level of fundamental assumptions. The ultramassive black holes we have been discussing tonight will eventually, on timescales of 10 to the power of 100 years or more, evaporate. The information paradox applies to them just as it applies to stellar mass black holes. But the timescale is so vastly longer than the current age of the universe that it is, for practical purposes, irrelevant to anything we can observe today. What matters today, what connects the theory to the observations, is the question of how these black holes formed, how they grew, and what they tell us about the early universe. And on that question, we are making genuine progress. Not fast enough to satisfy our curiosity, not fast enough to answer all the questions at once, but real progress, driven by new telescopes, new detectors, new computational simulations, and new theoretical insights. The James Webb Space Telescope is finding black holes in the early universe that are more massive than expected. The pulsar timing arrays are detecting the gravitational wave background from merging supermassive black holes. X-ray observatories are mapping the hot gas around clusters of galaxies and the feedback from central black holes. Radio telescopes are imaging jets from active galactic nuclei with unprecedented resolution. Optical and infrared surveys are cataloging the population of quasars and active galaxies across cosmic time. All of these observational threads are being woven together into an increasingly detailed picture of how the most massive black holes formed and evolved. And at the center of that picture, anchoring it, challenging it, and driving it forward, are the objects we have spent tonight with. the black holes that should not exist, the ones that are too massive for our models, too large for the time available, too extreme to fit neatly into our frameworks. Holm 15A star. Phoenix A-ton 618, which we discussed in a previous video, and which now takes its place alongside these others as one of the universe's most extreme achievements. These are not exceptions. They are not anomalies to be explained away with a footnote. They are the universe's most extreme self-expression in the domain of gravity. They are what happens when you give gravity 13 billion years and trillions of solar masses of material to work with. They are the end products of the most efficient process the universe knows for concentrating mass into the smallest possible volume. And they are sitting out there right now, at the centers of giant elliptical galaxies in the hearts of massive galaxy clusters, surrounded by the depleted stellar cores that record their merger histories, emitting faint X-rays and occasional jets, accreting one infalling star at a time, growing imperceptibly slowly toward futures we cannot see. The universe has been patient. It has taken billions of years to build these objects. We have been watching for decades and are only beginning to understand what we are seeing. The patience required to understand the universe is, in its own way, a kind of homage to the patience with which the universe built its most extreme structures. We will keep watching. We will keep measuring. We will keep building better instruments and developing better theories. And piece by piece, the picture of how these extraordinary objects came to be will come into focus. Until then, they sit in the dark at the centers of their galaxies, patient, massive beyond comprehension, growing very slowly toward a future that is longer than anything we can imagine. The universe made these things, and it made us curious enough to look for them and find them and ask why they exist. That might be the most remarkable thing of all. Sleep well. Somewhere out there, more than 1 billion light-years away, the most massive single objects in the observable universe are waiting quietly in the dark. They have been there for billions of years. They will be there for billions more. And we are the brief, improbable species that figured out how to find them. Good night. Let us go back to the beginning of all of this, back to before there were any black holes at all. Back to the very early universe, to the first fraction of a second after the Big Bang, when the universe was a hot, dense, almost perfectly uniform plasma of elementary particles. Because to truly understand why the ultramassive black holes exist and why they are hard to explain, you need to understand what the universe looked like before any structure had formed at all. In the first moments after the Big Bang, the universe was extraordinarily smooth. Measurements of the cosmic microwave background radiation, the afterglow of the Big Bang that we can still detect today, show us what the universe looked like about 380,000 years after the Big Bang, when it had cooled enough for neutral atoms to form. And what we see is a universe that was almost perfectly uniform in temperature across the entire sky. Almost perfectly uniform. But not quite. There were tiny fluctuations, temperature differences of about 1 part in 100,000, regions that were very slightly denser than average, and regions that were very slightly less dense than average. These tiny fluctuations were the seeds of everything that came after. They were the initial conditions for all of cosmic structure formation. Every galaxy, every cluster of galaxies, every filament of the cosmic web, every supermassive black hole, all of it grew from those tiny primordial fluctuations. Gravity amplified the fluctuations over time. Regions that were slightly denser than average gravitationally attracted surrounding material. they grew denser still. The surrounding regions were depleted, becoming voids. Dark matter, which does not interact with radiation and therefore started clustering earlier than ordinary matter, led the way. Dark matter halos formed first, and ordinary matter fell into the gravitational potential wells they created. The first stars formed inside these halos. The first black holes formed from the deaths of the first stars, or perhaps through direct collapse of massive gas clouds. This process of structure formation from small initial perturbations is called hierarchical structure formation, or bottom-up structure formation. Small structures form first, and larger structures form later through the merging of smaller ones. Small galaxies form, then they merge into larger galaxies. Small black holes form, then they grow through accretion and merge with other black holes. The largest structures form last, from the assembly of many smaller components. This hierarchical picture is one of the great successes of modern cosmology. The large-scale structure of the universe, the cosmic web of filaments, sheets, voids, and clusters, matches what simulations of hierarchical structure formation predict with remarkable precision. The distribution of galaxies across the sky, their clustering properties, the statistics of their masses and sizes, all of these are consistent with the hierarchical picture. But the ultramassive black holes at high redshift challenge the simple version of this picture. In simple hierarchical structure formation, the most massive objects form last. The largest clusters of galaxies are the youngest large objects in the universe, still assembling today from the merging of smaller clusters. But supermassive black holes of billions of solar masses were already in place when the universe was less than 1 billion years old. They were not among the last things to form. They were among the first. This does not necessarily contradict hierarchical structure formation in general, but it means that the specific pathway by which supermassive black holes form and grow must have been particularly efficient in the early universe. The dense, gas-rich environments of early galaxies provided conditions for accretion that are not available today. The higher merger rate in the early universe provided opportunities for growth that are rarer now, and the initial seeds, whatever they were, may have been larger than the typical stellar mass black holes we see forming today. Understanding the formation of the first black holes, the seeds from which all subsequent supermassive black holes grew, is one of the most active areas of research in astrophysics, and it connects directly to understanding the ultramassive black holes we observe today, because the most massive objects are in some sense the most extreme products of whatever the seed formation mechanism was. If we can explain how Holm 15A star got to 40 billion solar masses, we have learned something fundamental about the physics of black hole formation and growth across the entire history of the universe. There is one more thing I want to discuss before we close. It is something that does not come up often in popular discussions of black holes, but that seems to me important for putting the ultramassive black holes in their proper context. It is the question of what happens to a galaxy when its central black hole is this massive. A black hole of 40 billion solar masses, or 100 billion solar masses, is not just an interesting object sitting passively at the center of a galaxy. It is an active participant in the life of the galaxy around it. The feedback from such a massive black hole, even in its relatively dormant current state, shapes the evolution of the galaxy and the cluster around it. The most obvious manifestation of this feedback is in the hot gas that fills galaxy clusters. Clusters of galaxies are embedded in a diffuse atmosphere of extremely hot gas, heated to temperatures of tens of millions of degrees by the gravitational energy of the cluster potential. This gas radiates X-rays, and the X-ray luminosity of the cluster reflects the temperature and density of this gas. In the absence of any heating, the gas in the center of the cluster would cool over cosmic time. It would lose energy through X-ray radiation, cool down, become denser, and eventually fall into the center of the cluster, fueling star formation and black hole growth. This is called the cooling flow problem. Simple calculations suggest that the hot gas in the centers of galaxy clusters should be cooling rapidly and flowing inward, but observations do not show the expected star formation rates or the expected cold gas. Something is preventing the cooling. The leading explanation is AGN feedback from the active galactic nucleus, the accreting black hole at the center of the cluster. As the gas cools and flows inward, it feeds the central black hole. The black hole responds by producing jets, powerful collimated outflows of plasma moving at close to the speed of light. These jets punch into the hot gas of the cluster, inflating enormous bubbles or cavities of relativistic plasma and depositing energy in the gas. The energy from the jets heats the gas, compensating for the cooling and preventing a catastrophic cooling flow. This is a self-regulating feedback loop. Gas cools, feeds the black hole produces jets, the jets heat the gas, the heating slows the cooling, reducing the fuel supply, and the jet power decreases. The system oscillates around an equilibrium where the heating roughly balances the cooling. This is thought to be the mechanism that regulates the growth of the most massive galaxies and the most massive black holes in clusters. The most massive black holes, the ultramassive ones at the centers of the most massive clusters, are the most powerful drivers of this feedback. The cavities and bubbles inflated by the jets of these black holes can be seen in X-ray observations as regions of reduced X-ray emission, surrounded by bright rims of compressed hot gas. The energetics of these cavities, estimated from their size and the pressure of the surrounding gas, imply jet powers of extraordinary magnitude. Some of the most powerful jets known, driven by the most massive black holes, carry powers equivalent to trillions of solar luminosities, dwarfing the combined luminosity of all the stars in the host galaxy. This feedback is one reason why the largest galaxies stopped forming stars long ago. The powerful jets from their central black holes kept the gas too hot to collapse into stars. The black hole, by growing massive enough to produce powerful jets, effectively shut off its own fuel supply and the fuel supply for star formation in the surrounding galaxy. The galaxy froze in time, becoming the giant red elliptical we observe today, its stars aging together, no new ones forming, presided over by a black hole of incomprehensible mass sitting silently at the center. There is something almost poetic about this. The black hole grows by feeding on the gas of the galaxy. But in growing, it gains the power to heat the galaxy's gas and prevent it from cooling. The black hole effectively ends its own growth by becoming too powerful. And in doing so, it locks the galaxy into a particular configuration, a particular evolutionary state that it will maintain for billions of years, perhaps forever. The most massive objects in the universe are also the objects that most completely dominate and define the environments they inhabit. We have been on a long journey tonight, We started with the question of how black holes get so big. We traced the physics of black hole growth through accretion and mergers. We encountered the Eddington limit and the tension between that limit and the existence of massive black holes in the young universe. We talked about direct collapse black holes and Super-Eddington accretion as possible solutions. We visited Holm 15A star and its 40 billion solar mass black hole. We considered Phoenix A and its potentially 100 billion solar mass object. We talked about what these masses mean in terms of physical scale, in terms of event horizon size, in terms of their relationship to the galaxies that host them. We explored the gravitational wave background from merging supermassive black holes and the future observational windows that will let us study these events directly. We went back to the early universe and the seeds of the first black holes. And we ended with the feedback that connects the most massive black holes to the evolution of the largest galaxies in the universe. It is a lot to hold, but every piece of it connects to every other piece. The early universe and its initial seeds connect to the growth models and the tension with the Eddington limit. The growth models connect to the specific properties of Holm 15A star and Phoenix A. The properties of these objects connect to the depleted cores of their host galaxies, which connect to the merger histories that brought these black holes to their current masses. The merger histories connect to the gravitational wave background and to LISA and to the future of this field. And the most massive black holes connect back to the feedback that regulates the largest galaxies and the richest clusters in the universe. It is all one story, the story of how gravity, working over 8 billion years in an expanding universe seeded with tiny primordial fluctuations, built the most extreme objects that physics allows. Not just the most massive stars, not just the most massive galaxies, but the most gravitationally concentrated, the most extreme, the most paradoxical objects in the observable cosmos. Black holes that should not exist, and yet they do. The universe does not care about should, it cares about physics. And physics, applied consistently over billions of years to the initial conditions of the Big Bang, produced Holm 15A star, produced Phoenix A, produced Ton 618, produced every supermassive black hole sitting at the center of every galaxy in the observable universe, including the 4 million solar mass object sitting quietly at the center of our own Milky Way, 26,000 light-years from where you are sitting right now. We are embedded in a universe that made these things. That is what the universe does. It makes stars and galaxies and black holes and clusters of galaxies and cosmic webs of dark matter, and apparently, occasionally also curious beings capable of figuring out that all of this is happening and asking why. That combination, the universe's tendency to make black holes of extraordinary mass and its tendency to make beings who can notice them and wonder about them, seems to me one of the most remarkable things about the particular universe we happen to find ourselves in. We are going to keep noticing. We are going to keep wondering. And the black holes, for their part, are going to keep being there, patient and massive and ancient beyond our easy comprehension, at the centers of their galaxies in the dark. Good night. I want to take you somewhere that requires a specific kind of mental effort, not the effort of understanding a technical concept, but the effort of really holding a number, of not letting it slide past as an abstraction. There are certain numbers in astrophysics that we use so routinely that we lose track of what they actually mean. 1 billion light-years, 1 trillion solar masses, 10 to the power of 44 joules. We write them, we calculate with them, we cite them in papers and mention them in videos, and then we move on without pausing to let them land. I do not want to do that tonight. I want to pause on the number 40 billion solar masses and really let it land. The sun is a star. You know this. It is a ball of plasma about 1.4 million kilometers in diameter, held together by its own gravity, fusing hydrogen into helium in its core, generating the energy that makes life on Earth possible. It has been doing this for 4-6 billion years and will continue for another 5 billion years. It is, by any reasonable human standard, an enormous object. If you could replace the sun with a hollow sphere, you could fit 1-3 million Earths inside it. It contains 86% of all the mass in the solar system. Every planet, every moon, every asteroid, every comet, all of it combined is less than 0.2% of the solar system's total mass. The sun has a mass of about 2 times 10 to the power of 30 kilograms. That is 2 followed by 30 zeros kilograms. It is a number so large that it serves as the unit of measurement astronomers use for stellar masses. When we say a star has a mass of 10 solar masses, we mean it contains 10 times as much mass as the sun. When we say the black hole at the center of our galaxy has a mass of 4 million solar masses, we mean it contains 4 million times as much mass as the sun. Holm 15A star has a mass of 40 billion solar masses, 40 billion times the mass of the sun. 40 billion objects each containing 2 times 10 to the 30th kilograms. Multiply those together, and you get 8 times 10 to the 40th kilograms. That is an 8 followed by 40 zeros kilograms. The total mass of the observable universe, including all the dark matter and ordinary matter, is estimated at around 10 to the 53 kilograms. So the mass of Holm 15A star is a significant fraction of a tiny slice of the observable universe, compressed into a single object, behind a single event horizon. Now here is how to make that number feel like something. The Milky Way contains roughly a few 100 billion stars. If you could somehow weigh all the stars in the Milky Way, the total mass of stars in our galaxy is roughly somewhere between 100 billion and 400 billion solar masses. Let us say 200 billion solar masses as a round number. Holm 15A star has a mass of 40 billion solar masses. That is equivalent to 1/5 of all the stars in our entire galaxy, compressed into a single black hole. 1/5 of the Milky Way, squeezed behind one event horizon. That is what 40 billion solar masses means. It means that if you somehow took 1 in every 5 stars in the Milky Way and collapsed them all into a single point, you would have something comparable in mass to the black hole at the center of Holm 15A. Every 5th star you see on a clear night, gone. Every 5th star in the galaxy, removed, merged, collapsed, and the result would be one object. The event horizon of that object would have a radius of about 120 billion kilometers. The Earth orbits the Sun at a distance of about 150 million kilometers. So the event horizon radius of Holm 15A star is about 800 times the Earth-Sun distance. It is about 800 astronomical units. The outermost planet in our solar system, Neptune, orbits at about 30 astronomical units. So the event horizon of Holm 15A star extends to about 27 times the orbit of Neptune in radius. If you placed Holm 15A star where our sun is, its event horizon would extend far past every planet in the solar system and well into the Kuiper belt. We are not done. The distance from the Sun to the nearest star, Proxima Centauri, is about 424 light-years, or about 268,000 astronomical units. So the event horizon radius of Holm 15A star is about 800 astronomical units, compared to the nearest star distance of 268,000 astronomical units. The event horizon is about 0.3% of the distance to the nearest star, still small on interstellar scales. But the event horizon is a sphere, not just a radius. The volume enclosed by the event horizon of Holm 15A star is enormous. If you place this black hole in interstellar space, every planet, asteroid, and comet within a sphere extending 27 times the orbit of Neptune in every direction would be swallowed immediately. The solar system, if placed at the center, would be engulfed entirely, with room to spare. These thought experiments are uncomfortable. They should be. That discomfort is the right response to a number this extreme. The discomfort means the number is landing, and it is important that it lands because these objects are not hypothetical. They are not theoretical constructs or mathematical curiosities. They are real physical objects that exist in the universe right now. The event horizon of Holm 15A star exists. The mass is there. The curvature of spacetime is there. If you were somehow transported to within a few hundred astronomical units of the center of Holm 15A and you looked in the right direction, you would see the black hole's shadow, the dark region at the center of the accretion disk where the event horizon blocks the light from behind it. It would be an enormous shadow, larger than any object visible from Earth's surface, larger than the moon, larger than anything in our everyday experience of scale. But you would never see it, not from Earth. Not with any telescope currently in existence. Holm 15A is 700 million light-years away. Its angular size in the sky, enormous as it is in absolute terms, is still smaller than any current telescope can resolve when you account for that distance. The Event Horizon Telescope, which imaged the black hole shadows of Sagittarius A star and M87's black hole, achieves angular resolutions of tens of microarcseconds. Holm 15A star, despite being larger than both of those black holes in absolute terms, is so much farther away that it subtends a smaller angle in the sky. Imaging it directly is beyond our current capability, but we can measure it. We can infer its mass from the motions of stars in the surrounding galaxy. We can see the effects of its presence in the structure of the galaxy, in the depleted stellar core, in the dynamics of the surrounding gas. We can know it is there even if we cannot directly see it. That is one of the most remarkable things about modern astrophysics. We can characterize objects we cannot see directly, using the traces they leave in the things around them. And the traces left by Holm 15A star are extraordinary. The depleted core, the region where the stellar density drops off anomalously, is one of the largest ever observed. It has a radius of roughly 15,000 light-years. That is larger than the distance from the Sun to the center of the Milky Way, which is 26,000 light-years. The region of the universe that has been gravitationally disturbed by the formation and growth of this black hole extends over distances comparable to the scale of our entire galaxy. Think about the history encoded in that core. Every star that is absent from the central region of Holm 15A's host galaxy was ejected by the gravitational slingshot action of a merging black hole binary. Each missing star was once in the central region of one of the smaller galaxies that merged to build the current giant elliptical. When those galaxies merged, the black holes at their centers formed binaries, orbited each other, and gravitationally scattered stars out of the core. Each pass of the binary through the central stellar population ejected more stars. And gradually, the core was carved out, cleared of its original population, leaving the depleted region we observe today. The size of the depleted core tells us about the total mass ejected, and the total mass ejected tells us about the history of mergers. A larger core means more mergers, more mass ejected, more black hole growth through the merger process. Holm 15A star's enormous depleted core is a record of a violent merger history, a history of multiple major galactic mergers over billions of years, each one bringing new mass to the central black hole and clearing out more of the surrounding stellar population. This is astrophysics as archaeology. We cannot watch the mergers happen. They occurred billions of years ago. But the traces they left are preserved in the structure of the galaxy today, and we can read those traces like a geological record. The depleted core is a fossil of the galaxy's merger history, and from that fossil, we can infer the history of the black hole that created it. The same is true, in a different way, for other ultramassive black holes. Each one carries in its current properties, its mass, its spin, its host galaxy's structure, a record of its formation history. Each one is a data point in the story of how the universe built its most extreme structures from the initial conditions of the Big Bang. And we are in the process of reading that story. Measurement by measurement, observation by observation, simulation by simulation, we are assembling the narrative of black hole growth across cosmic time. It is not complete. There are large gaps. There are places where our models disagree with each other and with observations. There are objects like the ultramassive black holes at high redshift that do not yet fit neatly into any framework we have. But the story is emerging, and it is a remarkable one. A story of gravity working patiently over billions of years, amplifying tiny initial fluctuations into the cosmic web of structure, building galaxies from dark matter halos and gas, and at the center of every significant galaxy, building a black hole whose mass reflects the entire history of that galaxy's formation. We are part of this story. The Milky Way has a black hole. It is not as massive as Holm 15A star. It is not as dramatic as Ton 618. At 4 million solar masses, it is unremarkable by the standards of the most massive black holes in the universe. But it is there. Sagittarius A star, 26,000 light-years from where you are sitting, at the center of the galaxy you are embedded in. It has its own history, its own record of growth, its own relationship with the galaxy around it. And the same physics that produced Holm 15A star and Phoenix A produced Sagittarius A star, just with different initial conditions and a different history. We are not outside the story looking in. We are inside it. We are living in a galaxy organized around a supermassive black hole, part of a cosmos structured around the gravitational effects of billions of such objects. Observers in a universe whose large-scale architecture was shaped in part by the growth and feedback of the black holes at the centers of its galaxies. Understanding the black holes that should not exist is, in a way, understanding the universe that made us possible. The feedback from early supermassive black holes regulated the formation of galaxies and the formation of stars. The stars that formed in those regulated environments produced the heavy elements, the carbon and oxygen and iron and everything else that make chemistry and biology possible. The specific history of galaxy formation in our cosmic neighborhood, influenced by the growth of supermassive black holes, shaped the environment in which the Milky Way formed, and in which the Sun and the Earth came into being. We are, in a very real sense, the descendants of the physics that produced these extreme objects. Not directly, not in any simple causal chain, but embedded in the same physical history, shaped by the same processes, made of the same elements, forged in the same generations of stars that lived and died in the same universe that produced Holm 15A star. The universe that made black holes too massive to exist according to our models also made us curious enough to find them, measure them, and ask why they are there. That curiosity, that reaching outward with instruments and mathematics and imagination to understand the most extreme things the universe has produced, is itself part of the story, part of what the universe does with its matter and energy over billions of years of evolution. The black holes that should not exist are waiting in the dark at the centers of their galaxies. And we are here pointing our telescopes at them, measuring their masses, reading the archaeological records of their formation histories, building theoretical models to explain how they got there, and preparing new instruments to study the gravitational waves from the mergers that built them. That is who we are. That is what we do. And whatever answers we find, whatever picture of black hole formation and growth eventually emerges from the accumulation of observations and theory, the questions we are asking tonight will have been part of how we got there. Sleep well. The universe is 13.8 billion years old. It has been building these things for almost all of that time, and we have been watching carefully for a few decades. We are just getting started. Good night. There is a question that comes up whenever we discuss ultramassive black holes, and it is a question that sounds almost naive when you first hear it, but that turns out to be genuinely deep. The question is this: what is a black hole, really? Not in the sense of a technical definition. We have that. A black hole is a region of spacetime from which nothing, including light, can escape. The boundary of that region is the event horizon. Inside the event horizon, all possible future directions in spacetime point toward the singularity. There is no path that leads back out. Every direction is inward. That is the definition. But the question of what a black hole really is at a deeper level is still being worked out. And the ultramassive black holes we have been discussing push on that question in ways that smaller black holes do not. Here is one aspect of it. From the outside, a black hole looks like a region of intense gravity. You can orbit it. You can be attracted to it. You can measure its gravitational field, its mass, its spin, its charge. All of these properties are encoded in the geometry of spacetime outside the event horizon. The famous result from the 1970s, often called the no-hair theorem, states that a black hole in equilibrium is completely characterized by just three numbers: its mass, its angular momentum, and its electric charge. Everything else, every detail of how it formed, every piece of information about the matter that fell into it, is hidden behind the event horizon and cannot be recovered from outside. This is deeply strange when you think about it. You, sitting where you are right now, are made of atoms with specific structures, specific quantum states, specific histories. If you were to fall into a black hole, all of that information, every detail of your physical structure, would seemingly be lost. From outside the black hole, the only thing that changes is the mass, possibly the spin and the charge. Your information, the quantum state that defines you, is gone, not hidden, not stored somewhere. Gone. This conflicts with one of the most fundamental principles of quantum mechanics, which is that information is conserved. Quantum mechanics says that the evolution of a physical system is always in principle reversible. If you know the current state of a system precisely, you can calculate its past state or its future state. Information is never destroyed. The laws of physics are reversible. But if you throw information into a black hole and it disappears forever, information has been destroyed. This is the information paradox, and it is not a minor puzzle. It is a fundamental conflict between two of the most successful theories in the history of physics: general relativity, which predicts black holes and event horizons, and quantum mechanics, which forbids the destruction of information. Stephen Hawking, who discovered that black holes radiate thermally through quantum effects, initially thought this radiation was truly random, truly thermal, carrying no information about what fell in. If this were true, then when the black hole eventually evaporated completely, all the information it ever swallowed would be gone forever, definitively destroying quantum unitarity. In recent years, there has been significant theoretical progress suggesting that Hawking radiation is not truly random, that information is somehow encoded in the radiation even if we cannot easily extract it, that unitarity is preserved. This comes from developments in string theory and holography, particularly the idea that the physics inside a black hole is somehow encoded on its surface, the holographic principle. But the precise mechanism by which information escapes, how the interior quantum state of the black hole gets encoded in the Hawking radiation, is not yet understood. The ultramassive black holes we have been discussing will evaporate, eventually, through Hawking radiation. But the timescale is almost incomprehensibly long. The evaporation time of a black hole scales with the cube of its mass. A solar mass black hole would evaporate in about 10 to the power of 67 years. The current age of the universe is about 14 times 10 to the power of 10 years. So a solar mass black hole would last about 10 to the power of 57 times longer than the current age of the universe. For Holm 15A star, with 40 billion times the mass, the evaporation time is 40 billion cubed times longer than for a solar mass black hole. That is about 10 to the power of 97 years, 10 followed by 97 zeros years. The universe, as we know it, will be unrecognizable long before any ultramassive black hole evaporates. Stars will have stopped forming. The last red dwarfs will have burned out. All the stellar remnants will have cooled to near absolute zero. Even protons, if they are unstable as some theories predict, will have decayed. The universe will be a cold, dark, dilute sea of photons and leptons, and perhaps a few exotic remnants, stretching across dimensions vast beyond current comprehension due to the continued expansion of space. And in that cold, dark universe, the black holes will still be there. The ultramassive black holes, cooling imperceptibly slowly, emitting Hawking radiation at temperatures so far below the cosmic microwave background that they are effectively invisible, but still there, still massive, still trapping spacetime within their event horizons. They are, in a very real sense, the longest-lived objects the universe will ever produce. Not just the most massive, not just the most extreme, the most persistent, the most durable. when everything else has faded, when the last star has died and the last white dwarf has cooled and the last neutron star has evaporated into Hawking radiation, the supermassive and ultramassive black holes will still be there, quietly radiating away their final mass over timescales that make the age of the universe look like an eye blink. Eventually, even they will be gone. The last Hawking photons from the evaporation of an ultramassive black hole will be emitted after more time has passed than any number I can usefully write in this script. The universe at that point will be incomprehensibly old, cold, dark, and empty. And the last black hole's final moments will be a brief burst of high-energy radiation, the only event worth noting in that vast, dead future cosmos. But for now, they are here. 40 billion solar masses at the center of Holm, 15A 100 billion, perhaps, at the center of Phoenix A 66 billion, at the center of the host galaxy of Ton 618. These numbers, these objects, these events at the extreme end of the distribution of what the universe produces, are real and present and measurable. I want to bring you back to something concrete, to the question of what we actually know versus what we are inferring or modeling. We know that Sagittarius A star has a mass of about 4 million solar masses. We know this from decades of observations of stars orbiting the galactic center, using infrared telescopes that can see through the dust that obscures the center of the galaxy at visible wavelengths. We have tracked individual stars on complete orbits around the galactic center. We have measured their velocities and their positions with extraordinary precision. The mass of the central black hole is determined by these measurements with a precision of about 1%. It is not a guess. It is a measurement. We know that the black hole at the center of M87 has a mass of about 65 billion solar masses. We know this from stellar dynamics measurements similar to those used for Sagittarius A star, and we have the additional confirmation of the Event Horizon Telescope image, which shows a shadow whose angular size is consistent with this mass. For Holm 15A star, the measurement is less direct but still grounded in observation. The stellar velocity dispersion in the central region of the galaxy, measured using spectroscopy, is the primary data. The dynamical models that convert this velocity dispersion into a black hole mass carry larger uncertainties, but the measurement is not speculative. The mass is in the range of tens of billions of solar masses with reasonable confidence. For Phoenix A, the situation is more uncertain. The mass estimate is based on indirect arguments about the jet power and the accretion luminosity, methods that carry larger systematic uncertainties. The true mass could be substantially different from the commonly cited estimate. This is why I have been careful to note the uncertainty whenever I mention Phoenix A. This distinction matters. Astrophysics, like all empirical sciences, has a range of confidence levels. Some things we know extremely well, some things we know approximately. Some things we are making educated guesses about. The best science is clear about which is which, and adjusts claims accordingly. What we know extremely well is that supermassive black holes exist, that they span a range of masses from millions to tens of billions of solar masses, that they sit at the centers of large galaxies, that their masses correlate with the properties of their host galaxies, and that they grew through a combination of accretion and mergers over cosmic time. We know that the most massive black holes we have measured are difficult to explain by our standard models of growth starting from stellar mass seeds and accreting at the Eddington rate. and that some additional mechanism, whether larger seeds, Super-Eddington accretion, or some combination, is required. What we know approximately is the mass of Holm 15A star, the history of mergers that contributed to its current mass, and the physical mechanisms that drove its growth. The broad outlines are clear. The details remain to be worked out, what we are making educated guesses about, though educated guesses grounded in solid physical reasoning, is the mass of Phoenix A and the properties of the very most extreme ultramassive black hole candidates. These objects are real, but their precise masses are not yet measured with the confidence we would like. And what we genuinely do not know is the formation mechanism of the first black hole seeds in the early universe, the detailed process by which those seeds grew to the masses we observe today, the role of Super-Eddington accretion versus direct collapse versus mergers in explaining the high redshift massive black holes, and the ultimate fate of these objects over the incomprehensible timescales of the far future. That is an honest summary of where we stand. We know a great deal. We do not know everything. And the things we do not know are the most interesting things of all, because they are the questions that drive the next generation of observations, the next generation of theoretical work, the next generation of physicists who will spend their careers pushing the boundaries of what we know. The black holes that should not exist are a challenge to the field. They sit outside the predictions of the simplest models and demand explanation. That is exactly the kind of challenge that drives science forward. Every unexplained observation is an opportunity. Every anomaly is a clue. Every object that breaks the models forces us to build better models, and better models mean deeper understanding. We are building those better models now. We are designing the instruments to test them. We are training the next generation of astronomers and physicists to push further into the dark. The black holes at the extreme end of the mass distribution are not going anywhere. They are patient. They have been there for billions of years, and they will be there for incomprehensible times to come. And we are here briefly asking questions about them and piecing together answers. That is enough. That is more than enough. That is, in its own way, one of the most remarkable things in the universe. Sleep well tonight. Somewhere out there, the most massive objects the universe has ever produced are sitting quietly in the dark, at the centers of ancient galaxies, presiding over the stellar populations they shaped and the clusters they inhabit. They have been there since before the Earth existed. They will be there long after the sun has died. And in the brief window between those two eternities, we looked up and found them. Good night. Let us talk about what it would look like to approach one of these objects, not to fall in, not to cross the event horizon, which is a one-way trip with no return and no meaningful way to communicate what you found, just to approach. To come within, say, a few event horizon radii of Holm 15A star, and to look, you would not see a black sphere sitting in space the way you might imagine from the popular depictions. What you would see is something stranger and more beautiful. The accretion disk, if the black hole is actively accreting, would be a flattened structure of incandescent plasma wrapping around the equatorial plane of the black hole. The temperature of the inner disk, near the innermost stable circular orbit, the closest point at which matter can orbit a black hole without immediately falling in, would be far too hot for any ordinary matter to survive. The radiation from the inner disk would be intense beyond any human engineering to withstand. But set that aside and imagine you could observe safely. The accretion disk would not look symmetric, even if it were perfectly symmetric in 3 dimensions. The side of the disk moving toward you would be blue-shifted, its light compressed to shorter wavelengths, brighter. The side moving away from you would be red-shifted, its light stretched to longer wavelengths, dimmer. The asymmetry is dramatic. The approaching side would appear intensely bright, the receding side dim. Above and below the disk, space would be warped. Light from background stars and galaxies would be bent around the black hole, forming arcs and rings and multiple images. The famous Einstein ring, the complete circular image of a source perfectly aligned behind a gravitational lens, would appear as a bright ring of light around the black hole's shadow. And there would be additional rings, higher-order images of the same background sources, bent around the black hole by successively larger angles, appearing closer and closer to the edge of the shadow. The shadow itself, the dark region at the center where the event horizon blocks light from reaching your eyes, would be slightly larger than the event horizon. This is because the extreme gravity bends light enough that photons from slightly outside the event horizon also get captured. The shadow radius is about 2.6 times the event horizon radius for a non-rotating black hole, and slightly different for a spinning one. For Holm 15A star, the shadow, if you could see it from the right distance, would subtend an enormous angle. At a distance of 1 light-year from the black hole, the shadow would span several degrees across the sky. At the distance of a nearby star, say 10 light-years, it would still be a large object, visible to the naked eye as a dark disk surrounded by a bright accretion ring. You would not need a telescope to see it. You would just look at the sky and there it would be, this dark circle with a glowing ring, the most massive single object in the region of the universe you found yourself in. It would not be silent. Though space itself transmits no sound, the accretion disk would be a source of electromagnetic radiation across a vast range of frequencies. Radio waves, microwaves, infrared light, visible light, ultraviolet, X-rays, gamma rays, all of it pouring outward from the inner edge of the disk, from the material heated to hundreds of millions of degrees as it spirals inward. If you had detectors sensitive to these wavelengths, the black hole would be an overwhelming source, dominating the electromagnetic environment of the surrounding region. And the gravity, the tidal forces, the differential gravitational acceleration between one side of your body and the other, would be extraordinarily gentle at that distance. The event horizon of Holm 15A star is so large that even close to the horizon, the tidal forces are mild compared to those near a stellar mass black hole. This is one of the counterintuitive properties of ultramassive black holes. Their extreme mass does not translate into extreme tidal forces at the horizon. The tidal force at the horizon scales inversely with the square of the mass. More massive black holes have gentler tidal forces at their horizons. You could, in principle, cross the event horizon of Holm 15A star without any dramatic physical sensation. The crossing point would be invisible. There would be no visible boundary, no physical membrane, nothing to mark the moment of no return. That is perhaps the most unsettling thing about the event horizon. Not that it is violent, not that it is dramatic, but that it is invisible. You would cross it without knowing you had crossed it, and only later, as you tried to escape and found that every direction you turned, every path you could follow through spacetime led deeper inward, would you understand what had happened. There is no way out once you have crossed, not because some force holds you, but because the geometry of spacetime inside the event horizon is such that all possible futures point inward. Every path through spacetime that begins inside the horizon ends at the singularity. Outside the horizon, spacetime has its usual structure. There are time-like paths through space and time that correspond to possible trajectories for massive objects, and they can point in any direction. You can go toward the black hole or away from it. You can orbit it. You have choices. Inside the horizon, the geometry is different. The singularity is not somewhere in space inside the horizon. It is in the future. It is a moment in time, not a place in space. And all futures point toward it. You can no more avoid the singularity than you can avoid tomorrow. This is what general relativity says. At the singularity, the equations break down. The curvature becomes infinite. The theory fails. Something else must happen. But what that something else is, how the physics actually behaves at the singularity, we do not know. It is one of the places where general relativity stops being reliable and where quantum gravity, a theory we do not yet have in complete form, must take over. The ultramassive black holes are, in this sense, the largest possible laboratories for physics we do not yet understand. They contain, behind their enormous event horizons, regions of spacetime whose physics is beyond our current theoretical reach. The singularity at the center of Holm 15A star is shielded from our view by 120 billion kilometers of extreme spacetime curvature. We will never see it directly. We will probably never be able to test what happens there. But we can, perhaps, learn something from the Hawking radiation. If information is encoded in the thermal radiation emitted by black holes, as current theoretical arguments suggest, then the detailed spectrum of that radiation carries information about the interior. In principle, though not in any practical sense we can currently imagine, reading the Hawking radiation completely would allow you to reconstruct the entire quantum state of everything that ever fell into the black hole. The information is not lost. It is encoded in the most scrambled, inaccessible form imaginable in the radiation leaving the black hole. This is a profound idea. It means that the black hole, despite appearing featureless from outside, despite the no-hair theorem's assertion that only mass, spin, and charge are observable, is actually encoding an enormous amount of information in the quantum fluctuations of its Hawking radiation. The information is there. We just cannot read it. This connects to the holographic principle, one of the deepest ideas in modern theoretical physics. The holographic principle, which emerged from string theory and from the study of black hole thermodynamics, proposes that the information content of any region of space is proportional not to its volume, as you might naively expect, but to its surface area. The maximum amount of information that can be contained in a region is proportional to the area of the boundary of that region, measured in units of the Planck area, the fundamental unit of area in quantum gravity. For a black hole, the relevant surface is the event horizon. The information content of the black hole is proportional to the area of the event horizon, and this is directly related to the black hole's entropy, its thermodynamic entropy. The Bekenstein-Hawking entropy of a black hole is proportional to the area of its event horizon measured in Planck areas. For an ultramassive black hole like Holm 15A star, this entropy is staggeringly large. The entropy of Holm 15A star is roughly 10 to the power of 96 in natural units, a number so large that it dwarfs the entropy of the entire observable universe's ordinary matter. What does it mean for a black hole to have this much entropy? In thermodynamics, entropy is a measure of the number of possible microstates, the number of different ways the system can be arranged internally while appearing the same from outside. A high entropy system has an enormous number of possible internal arrangements. For a black hole, the enormous entropy reflects the enormous number of possible internal quantum states that are consistent with the same external mass, spin, and charge. All of those possible states look the same from outside. They are distinguishable in principle only through the Hawking radiation they emit. These ideas, the holographic principle, black hole entropy, the information paradox, quantum gravity, are among the deepest and most actively researched problems in theoretical physics. And the ultramassive black holes we have been discussing tonight are, in a sense, the most extreme versions of these puzzles. The largest black holes have the most entropy, the most information scrambled inside them, the largest Hawking radiation lifetime, and the most extreme tests of whatever quantum theory of gravity eventually explains what happens at the singularity. Understanding the black holes that should not exist is not just an exercise in cataloging extreme objects. It is probing the deepest questions in physics. Questions about the nature of space and time, about the relationship between gravity and quantum mechanics, about the information content of the universe, about what happens when matter is compressed beyond any limit we can currently understand. We are a long way from answering those questions, but we are asking them more precisely than ever before. With instruments of extraordinary sensitivity, with theoretical frameworks of great mathematical sophistication, with computational tools that can simulate the evolution of galaxy clusters and the growth of black holes across cosmic time, we are narrowing the gap between what we know and what we want to know. The universe has been patient. It built these objects over billions of years and has been waiting for something to notice them. We are, as far as we know, the first things in this part of the universe that can notice them, that can measure them, that can ask what they are and why they are there. That is a remarkable thing. And the objects themselves, the black holes that should not exist, are a remarkable thing. The most gravitationally extreme objects in the observable universe, the endpoints of billions of years of cosmic structure formation, the laboratories for physics we do not yet have, sitting quietly at the centers of their galaxies waiting. We will keep looking, we will keep measuring, we will keep asking, and eventually we will understand. Sleep well tonight. The universe is vast and old and full of objects that challenge our understanding. That is not a problem. That is the invitation. Good night. One more thing before we close. I want to talk about what the existence of these objects means for our place in the cosmos. Not in a mystical sense, not as a philosophical meditation, but in a very concrete physical sense. We live in the Milky Way galaxy. The Milky Way is a barred spiral galaxy with a mass of somewhere between 1 trillion and 2 trillion solar masses, including its dark matter halo. It is a reasonably large galaxy by cosmic standards, though not among the largest. It is part of the local group, a gravitationally bound collection of galaxies dominated by the Milky Way and Andromeda, with a few dozen smaller satellite galaxies. The local group is itself part of the Virgo supercluster, a larger structure that contains thousands of galaxies. And the Virgo supercluster is part of the Laniakea supercluster, an even larger structure, identified in 2014 that contains about 100,000 galaxies and stretches over 500 million light-years. At the center of the Virgo supercluster, about 54 million light-years from Earth, sits the Virgo cluster, the richest galaxy cluster in our immediate cosmic neighborhood. And at the center of the Virgo cluster sits the giant elliptical galaxy M87, with its 6.5 billion solar mass black hole, the first black hole ever directly imaged. We are embedded in a cosmic structure that is organized, at every scale, around massive objects and the gravitational potential wells they create. The Milky Way orbits the center of the local group. The local group falls toward the Virgo cluster. The Virgo cluster is part of a larger flow of galaxies drawn toward a massive concentration called the Great Attractor. And all of this structure, all of this hierarchical organization, emerged from the tiny initial fluctuations in the density of the early universe, amplified over billions of years by gravity. The supermassive black holes at the centers of galaxies are not incidental features of this structure. They are integral to it. They played a role in shaping the galaxies they inhabit through their feedback, their jets, their regulation of star formation. They are the products of the same hierarchical assembly process that built the galaxies themselves. And the most massive galaxies, the ones at the centers of the richest clusters, have the most massive black holes. The Milky Way has Sagittarius A star. The Virgo cluster's central galaxy M87 has its 6.5 billion solar mass black hole. The Abell 85 cluster's central galaxy Holm 15A has its 40 billion solar mass black hole. The Phoenix cluster has its potentially 100 billion solar mass black hole. Each one sits at the center of a larger and richer structure, and each one reflects the assembly history of that structure. We are downstream of all of this. The galaxy we live in was shaped by its merger history, by the growth of Sagittarius A star, by the feedback from that black hole, and from the stars that lived and died in the galaxy over billions of years. The heavy elements in our bodies, the carbon and oxygen and iron and everything else, were forged in stars that lived in the Milky Way or in its progenitor galaxies before they merged into the current structure. The entire cosmic history of our galaxy, including the growth of its central black hole, is encoded in the matter we are made of. And in the larger context, we are part of a universe whose large-scale structure was shaped by gravity working on dark matter and ordinary matter, regulated in part by the feedback from supermassive black holes in the largest galaxies. The existence of the Milky Way, in its current form, in its current location in the cosmic web, is a consequence of that larger history. The existence of the Sun, forming in a spiral arm of the Milky Way about 4.6 billion years ago, is a consequence of that history. The existence of the Earth and of life on Earth and of us is a consequence of that history. The black holes that should not exist are part of our history. Not directly, not causally in any simple sense, but as extreme versions of the same processes that shaped the universe we inhabit. They are the most dramatic expression of what gravity does when given enough time and enough mass to work with. And they are part of the context in which everything we know and everything we are came to be. That is not a small thing. That is the entire context of our existence, written in the language of gravity and spacetime, and the most extreme objects the universe has ever produced. We live in a universe that makes 40 billion solar mass black holes. We live in a universe that also makes curious beings capable of finding those black holes and asking why they exist. Both of those things are true simultaneously, and the conjunction of them is, to my mind, one of the most remarkable facts about the universe we happen to inhabit. The questions we are asking tonight are not separate from the story of how we came to exist. They are part of that story. The curiosity that drives the search for understanding, the drive to push beyond the current limits of knowledge, the willingness to sit with numbers too large for intuition and objects too extreme for everyday analogies. All of this is part of what the universe does when it produces minds. And the objects at the center of those questions, the black holes too massive to exist, the event horizons spanning hundreds of billions of kilometers, the depleted stellar cores recording billions of years of merger history, the gravitational wave backgrounds encoding the cumulative mergers of billions of supermassive black holes across the history of the universe. All of this is part of what the universe does when it has 8 billion years and the laws of physics to work with. We are here because of what the universe did over those 8 billion years, and we are asking about it. That combination, existence and curiosity, matter and mind, the universe and the beings it produced who study it, is the whole story. It is the only story there is. The black holes that should not exist are waiting in the dark. We found them. We are trying to understand them. And in trying to understand them, we are understanding ourselves and the cosmos we are part of. That is worth staying up for. Sleep well. The universe will still be here in the morning. The black holes will still be there, patient and massive and waiting. And so will the questions. Good night. There is a final thought I want to leave you with. It concerns not the black holes themselves, but the act of studying them. Science is often presented as a process of accumulating facts. You observe something, you measure it, you record the measurement, and now you know something you did not know before. That is part of it, but the deeper part is different. The deeper part is the process of building models, of constructing frameworks that connect observations to each other and to underlying physical principles, and then testing those frameworks against new observations to see if they hold up. The story of the ultramassive black holes is a story of this deeper process in action. We built a model of how black holes grow. The model was based on the best physics we had, the Eddington limit, accretion disk theory, stellar evolution, the growth of structure in the universe. We applied that model to the observations, and we found that it could not explain the most massive black holes at high redshift. The model predicted one thing, the observations showed another. The model needed to be extended, revised, improved. That is not a failure of the model. That is the model working correctly. A model that cannot be falsified, that cannot be tested and found wanting, is not a scientific model. The fact that our model of black hole growth makes predictions, and that those predictions can be compared to observations, and that sometimes the observations show us where the model falls short, that is exactly how science is supposed to work. The black holes that should not exist according to our models are not an embarrassment for astrophysics. They are a gift. They tell us precisely where our models are incomplete. They point us toward the physics we are missing, the mechanisms we have not yet included, the phenomena we have not yet understood. Every object that breaks a model is an arrow pointing at the next discovery. This is why the extreme end of any distribution is always scientifically interesting. Not because extremes are inherently important, though they often are, but because extremes test models in ways that typical cases cannot. The average supermassive black hole, sitting at the center of a typical galaxy, accreting at a moderate rate, can be explained by our current models without any difficulty. But the most massive black holes, the ones at the very end of the distribution, the ones that push past what our models straightforwardly predict. These are the ones that reveal where our understanding is incomplete. The history of science is full of examples of this. The anomalous precession of Mercury's orbit was a tiny deviation from the predictions of Newtonian gravity, but it pointed directly at the physics that general relativity needed to explain. The ultraviolet catastrophe, the failure of classical physics to correctly predict the emission spectrum of a blackbody radiator at short wavelengths, was a small discrepancy in a specific regime, but it pointed directly at the quantum nature of radiation. Every anomaly, every observation that falls outside the predictions of the current model, is a clue about what the next model needs to include. The ultramassive black holes are the current generation's anomalies. They are the observations that fall outside the simplest predictions of our growth models for high redshift massive black holes. And they are pointing us toward physics we do not yet fully understand. Direct collapse black holes, Super-Eddington accretion, the detailed mechanics of black hole binary mergers, the connection between the first black hole seeds and the large-scale structure of the early universe. All of these areas of research are being driven in part by the need to explain why the most massive black holes are as massive as they are. In 10 years or 20 or 50, someone will put together a more complete model. A model that includes the right seed formation mechanism, the right accretion physics, the right merger statistics, the right feedback prescriptions. And when that model is complete, the black holes that currently should not exist will fit naturally within it. They will no longer be anomalies, they will be explained, but by then there will be new anomalies, new observations from new telescopes and new detectors that fall outside the predictions of even the improved model, new objects at the extreme end of some other distribution, pointing at the next layer of physics we have not yet understood. That is how it goes. The frontier of science does not shrink, it expands. Every question answered generates new questions. Every model improved reveals new inadequacies at some other scale or in some other regime. That is not discouraging. That is the most exciting thing about science. The universe is not going to run out of things to surprise us with. It has been producing surprises for 8 billion years, and there is every reason to think it will continue to do so for as long as there are minds capable of noticing them and asking why. We are those minds. Right now, in this brief window of cosmic history, we are the universe noticing itself. We are the matter and energy of the Big Bang, organized over billions of years into structures capable of looking at the sky and asking what is out there and why it is the way it is. The black holes that should not exist are out there. We found them. We measured them. We are building the models to explain them. And when those models are complete, we will find the next thing that should not exist. That is the job, and it is the best job there is. Sleep well tonight. The universe is larger than we can fully comprehend, older than we can fully imagine, and stranger than we can fully predict. That is not a problem. That is the point. Good night.